Welcome to the explainer. Have you ever tried to describe something that isn't just a simple yes or no? Well, today, we're diving into fuzzy logic. It's this absolutely fascinating system that just embraces all those gray areas to help us talk about the world as it really is.
Just think about it for a second. When does a room officially stop being just warm and become hot? There's no magic number on the thermostat where that switch just flips, right? The real world is just full of this kind of ambiguity, and our simple everyday labels, well, they don't always cut it.
And this brings us right to the core difference in how we can approach logic. So you've got your traditional Boolean logic, which is kind of like a light switch. It's either on or it's off, a 1 or a 0. But fuzzy logic, that's way more like a dimmer switch. It allows for all the beautiful shades in between, what we call degrees of truth. So how does fuzzy logic solve this? Well, it introduces something called a membership value, a number anywhere between 0 and 1. So a room isn't just hot or not hot anymore. With fuzzy logic, we can say it's 0.7 hot, which gives it a partial measurable numbership in that hot category. Pretty cool, right?
All right, enough theory. To really see how this all works, let's get our hands on two sample fuzzy sets. We'll just call them A and B. Take a look here. See how each element has a totally different membership value in each set? We're going to use these exact sets for all of our examples, so keep them handy.
So let's kick things off with the three foundational operations. And hey, if you're already familiar with regular old Boolean logic, you're going to see that these have direct parallels to the classic and, or, and not operations you already know.
First up, we've got the union, which is basically the fuzzy version of OR. And the rule here could not be simpler. For any given element, you just pick the maximum membership value you see between the two sets.
So let's take element 10 as our first example. In set A, its membership value is 0.2. Over in set B, it's 0.4. All we have to do now is compare those two numbers.
And since 0.4 is the bigger number, the membership for element 10 in our new combined union set is 0.4. See? Simple. You just repeat that exact same process for every single element down the line.
Okay, next up is the intersection. This is our fuzzy AND. And as you've probably already guessed, we do the exact opposite of what we just did. This time, we're looking for the minimum value.
Let's check out element 20. Its membership in set A is 0.4, but over in set B, it's only 0.1. So for the intersection, we're going to put those two head to head.
The minimum of those two is, of course, 0.1, and that becomes our final result for element 20. So what this really tells us is the degree to which an element belongs to both sets at the same time.
All right, our last core operation is the complement. This is the fuzzy not. And you know what? It might be the easiest one of them all. To find the complement of any membership value, you just subtract that value from 1. That's it.
So, for instance, element 30 in our set A has a membership of 0.9, meaning it's very much a part of that set. Its complement is just 1 minus 0.9, which gives us 0.1. That tells us it has a really low membership in the not A set.
Okay, you got the basics down? Good, because now that we have that foundation, we're going to explore a couple of alternative operations that really show off the unique power and flexibility of fuzzy logic: bold union and bold intersection.
Now, bold union is another way to do an OR operation, but it's a bit more aggressive. What you do is add the two membership values together. But, and this is key, since a membership value can never be more than 1, the result gets capped at 1. This method really gives more weight when both values are pretty significant.
Let's walk through this with element 25. It has values of 0.7 and 0.9. So first, we add them up to get 1.6. But remember, our result can't be more than 1. So we take the minimum of 1 and that 1.6.
And there it is. The final membership value is just 1.0. This operation aggressively combines the memberships, sure, but it never ever breaks that fundamental 0 to 1 rule of fuzzy logic.
And on the flip side, we have bold intersection. This is a much, much stricter way of performing an AND operation. Here, you add the values together, then you subtract 1. And just like before, there's a safety net. The result can never, ever drop below 0.
Let's take element 10, with its values 0.2 and 0.4. We add them to get 0.6, then subtract 1, and we land at negative 0.4. But the formula tells us to take the maximum of that result in 0, so our final membership value is simply 0.0.
All right, To round out our little toolkit here, let's look at two final, super straightforward operations. First, checking if two fuzzy sets are equal, and second, how to calculate their product.
Now this is a really key point. The rule for equality is extremely strict. It's not good enough for some or even most of the values to match. For two fuzzy sets to be considered truly equal, the membership value for every single corresponding element has got to be a perfect match, no exceptions.
So looking back at our sets, A and B, we can tell instantly that they are not equal. We don't even have to look past the very first element. For element 10, the values are 0.2 and 0.4. Since they don't match, the sets are not equal. End of story.
And finally, we've got the product. This operation is exactly what it sounds like, and it's often used as another, slightly less strict alternative to that intersection we talked about earlier. For each element, you just multiply its membership value in set A by its value in set B, and that's your new value.
So all these little calculations we just walked through, finding the max, the min, multiplying, these are the fundamental building blocks for some incredibly complex and powerful systems that run our modern world. And now that you know the basics, the real question is, where is this fuzzy thinking already hard at work all around you?